Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. Thank you for being here. I'm very, very happy to be with you today and for the next few days. Today's lecture will introduce something that's very unfamiliar, probably, to most of you. And so I'm going to start off gently, not too intense. We'll get more intense over the next few days. Please do ask questions, because if you don't understand the basics at the beginning, the rest is completely lost. So I'm going to talk about a relatively new topic, differential privacy. Formally, I think the first paper that used this term was in 2006, but really the research began a bit earlier than that, 2002, 2003. So I call this the sanitization pipe dream. In this dream, and I have smoked on this pipe, I know about this dream, we start with a database that's shown in green. It contains a lot of very personal information about many different people. And the hope is that somehow a data curator, represented over here, can sanitize this data set, can strip out identifying information, and release to the public a sanitized database over here, which allows a data analyst to study the population, to learn things about humanity as a whole, while protecting the privacy of the individuals whose data are in the original database. So we call this the sanitization pipe dream. And there are many obvious motivations for it, like analyzing census data. Where do we live in the country? What is the distribution of the ages in the population? Where do we need new schools? Which areas of the country are underrepresented and need more representation in government? Or we might want to be studying medical outcomes. Which therapies for a particular illness were successful? Which ones caused very unpleasant side effects? We might be looking at genomic information. Which locations in the DNA seem to be related to having a particular genetic trait or an illness? Now, in the sanitization pipe dream, once this yellow sanitized data set is released, we don't need the curator anymore, and we don't need the original database. This yellow set contains the answers to all of the sort of statistical questions that the analyst might want. Okay. Now, this is a very, very difficult problem. And it's difficult even if the curator is perfect, brilliant, trustworthy, well-meaning, successful. It's also difficult if the data are stored in a vault and there's absolutely no problem with physical security or somebody breaking in and looking at it. And so for the rest of this talk, we're going to assume that the curator is in fact perfect and has unbounded computational ability. And we will assume that the data are perfectly secure, and we are concerned with privacy loss in the correct functioning of the curator and the protection mechanisms. Now, you might say, one of the reasons this is hard is that this yellow sanitized database that we had was required to answer all possible future questions. And that makes it very, very hard because it's really difficult to anticipate what are those questions. So you could say, let's try maybe for something that could be easier. So we will interact. And the analyst will ask a question, the curator will go and consult with the data, compute some kind of answer, maybe jiggle the answer a little bit to protect privacy, give a response, and then they interact in this way. And even so, it still turns out to be a very, very difficult problem. Now, many people, when they first hear this problem, say, I know how to answer this. And there are certain ideas that we just have to get out of the way so that they don't distract you for the rest of the talk. So let's deal with them now. The first is only allow queries about large sets of individuals. That is, don't allow a query that says, does Cynthia Dwork have the sickle cell trait? But instead, insist that the questions are over large sets. And this doesn't work. So for example, it falls to what we call a differencing attack. Consider just two questions. The first one is, how many Microsoft employees have the sickle cell trait? That means one gene for sickle cell anemia. So how many Microsoft employees have this trait? And then the second query is, how many Microsoft employees, other than the director of the Silicon Valley lab, have the sickle cell trait? Both of these are very large sets of people. But if you knew the exact answer to both questions, you could subtract one from the other, and you would find out whether my director has the sickle cell trait. The next suggestion is just add random noise to the true answer. Now, that's not necessarily a bad idea, and we will get back to randomness, but you have to be careful. Suppose we add fresh random noise every time a query is answered. So if you ask the same question over and over again, you can average the responses that you get, and you will hone in on the true answer. And now you can launch the first attack again. Now, some people say, oh, well, if you see that it's the same question that gets asked, give the answer you gave last time. Don't use fresh random noise. And that's a really, really good idea. But if the query language is very rich, then it's undecidable to determine whether two queries are in fact the same. So it has some merit, but there are some real problems. And another suggestion is keep track of every question and answer that has taken place. And if you see that answering this next question is going to cause a privacy compromise in light of everything that's been done so far, then don't answer it. And the problem with that is that sometimes just by the curator saying, no, I can't answer that, it's not safe, the analyst can figure out something that would be a privacy violation. Okay, so we got rid of these, we took care of these. Now, there's a very unfortunate reality, and that is that a sanitization cannot be too accurate. So in 2002, I started thinking about privacy in statistical databases. So did separately Dinur and Nissim. And they were looking at the following question. They didn't have a definition of privacy. But they said they were interested in knowing just how distorted answers would have to be in order to protect privacy. So they formalized the problem as follows. And the formalization sounds really silly, but it turns out that it isn't. Just trust me on that, and later, if we have time, I'll explain why it isn't. Suppose the database is just a single bit per person. So really, everybody in this room is listed in alphabetical order, and for each of us, there is a secret bit, say our HIV status, or whether we have the sickle cell trait. And we look at the set of queries which are simply subsets of the rows of this database. That is, subsets of the people in this room. And the semantics of the query is, in that subset, how many people have the bit set to 1? In other words, what is the sum of the entries in the database for this selected set of rows? And the system is going to respond with the true answer plus some noise. And Dinur and Nissim wanted to know, how much noise do you have to add to protect privacy? But they didn't have a definition of privacy. So they said, well, we don't know what privacy is, but here's something that everybody will agree is not private. So I actually named it blatant non-privacy. So blatant non-privacy is when the adversary, the analyst who has been interacting with the database, writes down a candidate database, its guess, and it guesses correctly almost everywhere. Yes?
I'm not really sure what you mean by noise.
So the answer is a number, right? And we choose, according to some probability distribution, we choose another number, that's the noise, and we add it to the true answer, and we release the result.
The sanitizer does that.
The sanitizer would do that, right. Okay. So are you all familiar with this notation, little o of n? So less than linear in n. So blatant non-privacy is when the adversary can guess more than 99.99% of the bits. Okay. And their theorem, which we will prove, shows that if all of the responses are within little o of n of the true answer, then the algorithm is blatantly non-private. So it's not enough to add noise that's scaled something like square root of n or n to the 2/3. That will not give you privacy, cannot give you privacy. Now, this particular attack, wait, what is one of the conclusions that we have to draw from this? It's impossible to release that yellow sanitized database that will answer all future questions with non-trivial error. Because if so, then it would provide answers that were all good, to within little o of n. That's what non-trivial error would mean. And so the attack here would work. Okay. Now, this particular attack is kind of ridiculous because it turns out that in this particular attack, the adversary has to ask all 2 to the n subset queries. And Dinur and Nissim then said, well, what about a realistic adversary? And the realistic adversary runs in polynomial time. And they showed that even such an adversary that actually asked only n log squared n questions, and the questions were random, so each element was included with probability 1/2, even that is blatantly non-private. And in fact, it isn't even necessary that all of the answers be within the stated error bounds. Here's a theorem. Again, it asks few queries, but it requires a lot of computation. That says if just a little bit more than half of the queries have small error, little o of root n, then the algorithm is blatantly non-private. So if almost half of the queries can have arbitrarily large error, there is still an attack on the privacy. Okay. Yes?
A question for the previous theorem. What does it mean to the answer to be within ON of the true answer? Or what is the metrics on answers?
So the answer is always a number between 0 and n, because we're asking how many people. The true answer is always a number between 0 and n. Now we're going to add some random number to that, and the question is how big is that random number? Okay?
It's additive, not multiple.
Yes. Okay, so the first theorem actually has a very, very simple proof. So let's look at our database, and let's assume that we have a bound E on the absolute value of the error. So there's a true answer, maybe it's n over 6, and then we add a number. That number might be positive, it might be negative, but let's say that we have a bound E on what that absolute value is. Okay, so the adversary runs in 2 steps. First, it's going to get an estimate on the number of ones in every possible set by asking for every set how many in there have a 1. And our mechanism, our curator is K in this picture. The curator's names will change from C, K to M. I think that covers all of them. All right? And so the promise is that the error bound, the difference between what the curator says and the true answer is E, is bounded by E, okay? So first the adversary asks all these questions, and then the adversary sits there and thinks. And what does it do when it thinks? It goes through in its mind every possible length n binary vector, and it weeds out the distant ones as follows. For every possible candidate database, C, it checks to see, is there a set S on which the answer I got differs by more than E from what the answer is on C? If so, then I throw out C. If I find a C for which it's always less than or equal to E, then it reports that candidate C. And notice that since the curator always stays within E of the truth, the real database will not be weeded out. So there's always going to be some answer. And now we claim that the distance between the Hamming distance, the number of locations on which C and D differ, is bounded by 4E. So to see that, I've rearranged the database D. I have a bad echo here. I've rearranged the database D so that we have the zeros all here and the ones all here, okay? So what happens when we ask on this set? Well, C wasn't eliminated, so C has at most E1s on that set. Similarly, D, it has 0 ones, but the reported will be at most E. So the difference between how many ones C has and D has in there is going to be at most 2E. And the same thing is true over here on the set S1, where the database is all ones. So add up the errors, we get 4E. Okay? Yeah?
So is it like distance between the C and the K?
Yeah, I was using the Hamming norm. What?
Triangle inequality gives you a better bound?
Sure, but this is fine. I'm just trying to show that if your error is always little o of n, then you will reconstruct to within 4E. So it's still reconstructing to within little o of n. Okay. Now, I'm going to just kind of hint at what happens in that second theorem, where we said that strictly more than half of the queries had error that was little o of square root n. Now, the queries are going to be random, and it's better to think about now that the database, instead of being 0, 1, is plus minus 1. So plus 1s and minus 1s. And so let's fix our database and look at a random vector R. All right? So for a random R, the inner product, so here's my database X in blue, and here's R. The inner product is the sum of IID plus minus 1 random variables. So there's going to be some constant probability, so that the probability over choice of R, that somehow, the probability over choice of R, the inner product of X and R will be at least on the order of square root n, at least a half root n, okay? Now, suppose the database is X again, and Y is a candidate vector that disagrees with X on at least some constant C times n number of locations. Then, by exactly the same reasoning, there's some chance that the random vector R will separate X and Y in the sense that the inner product with X is far from, that is on the order of square root of n, the inner product with Y. And so with some constant probability, a random query will weed out a nearby database Y. Okay? And then you use linearly many queries and a union bound to argue that you're going to, with high probability, knock out all nearby databases Y. So that's just the intuition for how this argument goes. Okay. So now you're already discouraged because you can't really answer with very small error, it seems. And now I'm going to discourage you even more because there's this sort of litany, like a religious ritual that all talks about privacy on real live databases has to go through. And since you're having a course on privacy, you need to know this religious ritual. So some of these are so well known, they have short names. This one is called the AOL debacle. I don't know why this is called a debacle, but it's called a debacle. Okay. So what happened here, a New York Times, so AOL, America Online, decided to publish supposedly anonymized query histories of individuals. And the New York Times took this anonymized queries and they managed to figure out one of the people who was associated with a set of queries. So that was that. People were fired. They lost their jobs for having done this release. The next one has the short name William Weld's Medical Records. William Weld was the governor of Massachusetts. A regulation was passed saying that health maintenance organizations needed to release to the public medical encounter data, telling for the visits for the people treated at this HMO, certain information, their ethnicity, when did they come, what was their diagnosis, what procedure was done on them, what medications were they given, how much did they pay, what was their zip code, their birth date, and what sex were they. So LaTanya Sweeney, who was a graduate student at MIT at the time, got hold of, for a small amount of money, I mean, it's tens of dollars, I think it was, voter registration data for Cambridge, Massachusetts, which is where MIT is. That data set contains for each person, each registered voter, name, address, date of registration, party affiliation, when did they last vote, and zip code, birth date, and sex. And she was able to cross-link these and identify the medical records of the governor of Massachusetts. Okay. Netflix prize. So Netflix, you all know what Netflix is? Yes? Right. So Netflix has a movie recommendation system that recommends movies to its users. And they wanted a better recommendation system. So rather than paying employees to design a better one, they said, let's have a competition. So they published a bunch of anonymized data records. Here's from their rules page. This was a set of training data. Because why? You want to help them build an algorithm that's going to do better recommending. You have some ideas about how to do this. You need some test data to train your algorithms on and to test your algorithms against. So they needed to publish some test data and training data. So here's what they said. It consists of more than 100 million ratings from over 480,000 randomly chosen anonymous customers on nearly 18,000 movie titles. And they said that to protect customer privacy, all personal information identifying individual customers has been removed. Okay, so could they really do that? Here's a source of auxiliary movie information. Just as with the HMO records, there was this extra information, which was the voter registration set. Here, the extra information is the Internet Movie Database, where individuals can register for accounts and rate movies. They don't have to do this anonymously. They can do it anonymously if they wish, or they can use pseudonyms, or they can use their real names, and many people do. And things that they make public includes the ratings, the dates, and their comments on the movies. And here's what Narayanan and Shmatakov did. They noticed that with 8 movie ratings, of which we allow 2 to be completely wrong, and dates that may have a 3-day error, 96% of Netflix subscribers whose records have been released can be uniquely identified in the data set. In other words, when you rate movies on Netflix, you're also somewhat likely around the same time to rate them on the IMDb if you're doing both. And there are lots and lots of movie titles, so the selection of just a couple of them really narrows us down. For 89% of all people, 2 ratings and dates are enough to reduce the set of plausible records to 8 out of almost 500,000. Okay, so they did this. And what happened? Well, first of all, they drew some very unflattering conclusions about a named person in IMDb. They said that he was homophobic, for example. Now, here's a really interesting point, which the statistician Steve Feinberg always emphasizes. Once this happens, they might be right, or they might be wrong. And either way, that man was harmed. Netflix wanted to run a second competition. They liked the results that they got from the first competition. They wanted to run a second competition. There was a lawsuit. A woman, a lesbian, sued to prevent it. She said, I'm a lesbian. If my employer finds out that I'm a lesbian, I will be in big trouble. I will lose my job, or I will have an unpleasant work. I don't remember. And as a result of this lawsuit, Netflix decided not to have their second competition. Okay. Here's one that was only on paper. A certain company, not Microsoft, I had heard was going to release its social network graph. Social network graph, right. So social network nodes are people and edges represent social relationships between them. For example, email messages that have gone one direction or the other. And here's what we call an active attack. Here, the attacker knows that the thing is going to happen and maybe does something. So what does the attacker do here? It creates a graph, like it signs up just as you can on Gmail or Yahoo or Hotmail or whatever. You can sign up for new accounts. So here it creates about 12 new accounts, a small number of new accounts. And it creates artificially some social links between them by sending mail back and forth, for example. And so this graph that it creates, this little graph that's often the light blue on the side, it's highly interconnected among itself, but it's very lightly connected to the rest of the graph. Specifically, suppose I want to find out whether 2 people, let's call them S and J, are communicating. I want to know whether they're friends in the social network. So what I do is I create this little light blue graph over here. I connect one node to S by writing to S. I connect another node to J by writing to J. And now the anonymization happens and the anonymized social network graph is released. Okay? And then there's this magic step which involves creating a Gamma-Ray-Hu tree, what's called the Gamma-Ray-Hu tree, which, roughly speaking, allows me to isolate lightly linked in subgraphs from the rest of the graph. And then on top of that, I use some special whoa, I'm missing a slide. Okay, oh no, there it is. I use some special subgraph, some special structure of my subgraph that allows me in the just giant anonymized shmush that was released to find A and B. From that, I go and I look for S and J, because that's the only people they're connected to, and I see, are they connected? Okay. Now, there are other attacks that are beyond re-identification, and I think this is a very important point because whenever you talk to people who really do release data sets for public access, they always talk about, is it easy or is it hard to trace a record back to the individual, to re-identify an anonymized data item? And the point that I want to make on this slide is that there are worries beyond re-identification. So for example, let's look at the medical encounter data situation. I have an elderly neighbor. An ambulance comes and collects her at night. I see the ambulance. I know that she has gone to the hospital. The next day, I look at the published medical encounter data for the night before. Now, it turns out, I don't live in a very big town, and it turns out that the union of the troubles for which elderly people were admitted the night before is just 4 things. Tachycardia, that's very, very fast heartbeat, influenza, a broken arm, and a panic attack. So any elderly person who went to the hospital last night had one of those 4 problems. I immediately learn that my neighbor had one of those 4 problems. Moreover, when I see her, she seems fine, so she doesn't have influenza and she didn't have a broken arm. That means I now know that she had either tachycardia or a panic attack. And in fact, those 2 could be related. So it's a privacy problem, and it isn't re-identification. I don't know which record is hers. There may be 6 people who had panic attacks and 3 people who had tachycardia. I don't know which one's hers, but I know that she's one of those 9. And therefore, I know that she had one of those 2 symptoms. So re-identification, the question of re-identification didn't actually capture the real privacy risk, which is this stuff that I learned about my neighbor. And there's one more example, which is a tremendously important example. This comes from the medical community. It's a list of 10 authors, and I don't know any of them, and everybody calls it the Homer et al. Example. And it goes like this. The context for this is the genome-wide association study. So let's assume for simplicity that we, instead of being dual-strand DNA creatures, that we were just single-strand DNA creatures. So we're represented by a single strand of A, C, G, and T. Okay? Now, if you look at the DNA sequence for everybody in this room, on most locations, we will all have exactly the same protein. But there are certain locations in which there is variation in the population. And those are called SNPs, for single nucleotide polymorphism. Polymorphism meaning multiple forms. All right? And typically, what happens there is that, say, most of the people, 95%, 97% might have, say, a C, and the other 3 or 5% will have a T. The popular version is called the major allele, and the unpopular one is called the minor allele. So in a genome-wide association study, the researchers are looking for locations in the DNA that seem to be associated with the illness or some particular trait. So for example, the trait of becoming a smoker later on in life. I mean, I actually know somebody, there's a Microsoft researcher who was looking for what he called the smoking SNP. Okay? So you take this population, you divide it into 2 groups. Let's say the smokers and the non-smokers, or the case group of people who have been diagnosed with an illness versus the control group, which is the healthy group. And you're looking for places where there's variation in the major and minor allele frequencies. So maybe in the healthy group, in some particular SNP, 5% of the people have the minor allele, but in the case group, only 3% have the minor allele. That would be the kind of thing they would be looking for. Okay, so the only thing that is released are the statistics. what fraction in the case group had an A, what fraction in the control group had an A, and so on. Just the statistics. No names, no structure, just the statistics. And what they showed was the following. Suppose you took this and you sequenced my DNA. I've been drinking from this. You sequenced my DNA. They showed that there is a statistical test which makes it possible to determine whether or not I'm in the case group. So not, let's say, whether my DNA looks like somebody who might be sick, but no, whether I was actually in the case group, meaning that I was diagnosed as having the illness, okay, which is a tremendous privacy compromise. As a result of this pen and paper exercise, because this was not carried out in practice, as a result of this, the US National Institutes of Health changed their publication policies regarding statistics that were computed on the data in the studies that they funded. So these things have an impact. Okay.
Is that just one shot? Just one result of one study, or do you duplicate this?
They did it based on one study.
Just one. So if I just have the statistics from one study,
If you listen to the next couple of days of lectures,
then I'll realize
it'll start to seem, duh, of course. All right. So let me try to point that out. If you haven't figured it out by the third day, ask me and I'll push on it again. I'll just show you. You know, like when I saw this, I said, well, I know why this happens. Yeah. Okay. I know why this happens, but okay. But it's very powerful. Okay. Now, when I talk to people who really work with data and who really work with this kind of confidential data, they'll say, but how much effort, you know, and you're just hurting a few people. Maybe it doesn't matter. Maybe it's okay. Maybe we should do these things which, you know, aren't perfect privacy because really just a few people will be hit. It's not a crazy point of view. You might say that the social benefits of the particular research maybe merit this risk to privacy. But if you're going to take this approach, you could also say the following. Here's my database. Each line is a patient, let's say. Why don't I just randomly sample a couple of rows and release those rows in their entirety? Learning theory tells us that all the statistical information we want really should be present there. Okay? Is this okay? I'm not saying it isn't. Again, there could be situations for which this is the right thing to do. And it's a sort of a moral and a philosophical question. There are people who advocate, take my medical data, use it to help people. Right? Perfectly reasonable point of view. But if you think it's okay, then there's no reason to sit through the rest of the course. It's only if you think it's not okay, or if you're interested in the cases for which it is not okay, that the rest of this course is addressed. All right. Okay. So, I gave you several examples of kind of privacy attempts that went wrong. And there are many more in the literature. Many of them that are just intellectual exercises. They weren't, say, things that happened and you read about them in the popular press. They all were, in my opinion, definitional failures. It's not that the implementation of the definition of privacy wasn't carried out well. It was that the definition of privacy was maybe syntactic or ad hoc, and it didn't really capture everything that we wanted when we really thought about what are the possible harms. So when I started getting interested in this, I said, okay, let's go back to a place where there was tremendous definitional success in cryptography. And that was what we called semantic security of a crypto system, an encryption system, against an eavesdropper. So this is a definition due to Goldwasser and Micali. It was tremendously important in cryptography and theoretical computer science, complexity theory. So we need just a little bit of vocabulary. One of these words you've already heard. The plain text is a message that's going to be transmitted. This person is sending a message to that person. The message is M in this picture, and that's the plain text message. The ciphertext is an encryption. That's C in this picture, obtained by applying an encryption algorithm to M. And then there's auxiliary information. You have heard about auxiliary information already. That was, for example, the Internet Movie Database or the voter registration records. So auxiliary information is just anything else known to the attacker. Here's my attacker. She hears the encrypted transmission, and she receives from a carrier pigeon some auxiliary information. So what Goldwasser and Micali wanted to say was that the ciphertext leaks no information about the plain text. But, you know, if this encryption is uniquely decryptable, if there's only one way to decrypt it, then it has all of the information about the plain text. So how could they possibly say this? Well, they formalized it as follows. They compared the ability of somebody who is computationally bounded, who sees the auxiliary information and the ciphertext, so in other words, this detective over here, they compared the ability of that person to guess something about the plain text to the ability of somebody who only sees the auxiliary information and doesn't actually get to see the encrypted transmission to do the same thing. And they said this difference should be very, very tiny. In some, you know, we call it cryptographically small. And this is just a brilliant, brilliant definition. And it completely captures the notion, a realistic way in which we're saying the ciphertext doesn't leak anything, doesn't leak anything that can be used. Can you come up with a similar definition for statistical databases? This is, of course, the first thing I tried, but I wasn't the first person to try it. In 1977, 5 years before Goldwasser and Micali came up with their definition for encryption, Tordellinius, the statistician, was thinking about similar problems to what I was thinking about. And he said the right definition for privacy in what he was calling a statistical database, one that lets you learn statistics about the population, is the following. Anything that can be learned about a respondent, that is somebody who answered questions and had their data included in the database. Anything that you can learn about a respondent from the statistical database can be learned without access to the database. It's exactly the definition of semantic security. And you can formalize it exactly that way, which is really nice. But the first thing is, it's unachievable for good and bad reasons. So, first of all, we clearly can't achieve cryptographically small levels of tiny. And the intuition is the following. Unlike in the previous slide, where the legitimate receiver of the message is supposed to learn the whole message and the eavesdropper is supposed to learn nothing, here the eavesdropper and the legitimate recipient are the same person. They're the data analyst. They have good reasons for analyzing data and trying to get information, and they might have bad reasons. They might be malicious. So the analyst and adversary is supposed to learn some things. That's why we have a database in the first place. For example, it should be able to distinguish a case in which, say, all men in the population have a certain disease and no men in the population have the disease. That's the whole point. You're trying to find out these things. Okay, so you have to be able to learn some unpredictable things. So this just said, well, can we relax the notion of tiny? That's the only possibility for help. And the answer is no, you can't do that either. And now we're starting to get to the meat of the problem, which is that anything that looks anything like this is going to be unachievable in a useful database. So let's say that I have come from Mars, and I have some erroneous beliefs about human beings. For example, I think that all human beings have 2 left feet. I don't know about people. I think everybody has 2 left feet. And my database teaches the very natural and obviously not privacy compromising statement that no, most people have 1 left foot and 1 right foot. And now my view of, say, Alan Turing, my guess about the feet of Alan Turing has changed dramatically. I used to believe that he had 2 left feet, and now I'm pretty sure he didn't have 2 left feet. Okay. Formally, what happens is you can extract from the database something called a one-time pad, and you can set the auxiliary information to be the pad plus a privacy violation. Then the data analyst who has access to the database can learn the one-time pad and peel it off and get the privacy violation. But the other party who only has access to the auxiliary information learns nothing. Now, a really important thing in that example with the 2 left feet was that the database taught something. And this is the most important thing I'm going to be saying today. We are interested in databases that teach. So suppose we have a database that teaches us that smoking causes cancer. That's what we learn from studying the medical data. Now, let's look at an American smoker. The smoker's insurance premiums, how much they have to pay for medical insurance, goes up because the insurance company also learns that smoking causes cancer and therefore charges the smokers more because they think that they may have to pay for their medical treatment later. So the smoker was hurt because the insurance premiums rose. But of course, learning that smoking causes cancer is exactly why we want to be able to analyze medical data. This is exactly the kind of thing we want to learn. And in fact, because of this, the smoker enrolls in a smoking cessation program. So the smoker is also helped. Now, here's the interesting thing. This smoker was harmed and helped independent of whether or not he was in the database. He was harmed or helped by the fact, the teachings of the database, not about his participation or lack of participation. And this is where we start to get the definition of differential privacy. What we want to do in differential privacy is limit the harms to the teachings of the database, not somebody's participation in it. In English, the definition is going to say that the outcome of any statistical analysis is essentially equally likely. And my probability space here will be over the coin flips of our well-meaning curator. Is essentially equally likely, independent of whether any individual joins or refrains from joining the database. You want to learn approximately the same thing, either way. If this is true, and I'll get back to these points again and again, we'll immediately neutralize all linkage attacks, statistical attacks, leveraging attacks, all of these things that I've been showing you. So here's the formal definition. There's a parameter called epsilon. Okay. Most of the time when you see this, you're not going to see an epsilon here. You're going to see the pair epsilon comma 0. I don't know why I missed this one. All right. So M is going to be a mechanism. I told you that the curator would sometimes be called K, sometimes C, sometimes M. There's history that explains this. And I didn't bother to bring all the slides to the current date. But a mechanism M gives epsilon differential privacy. What? If for all pairs of adjacent databases, what do we mean by adjacent? Remember the English language definition, that the distribution on outcomes is essentially the same thing whether any individual joins or refrains from joining. Those are adjacent databases. One database and the other one, which is just slightly smaller, So the bigger one contains the smaller one and has the data of just one more person. Those are adjacent databases. Okay, so for every pair of adjacent databases, X and X prime, for every possible event, that is subset C of the outputs, the chance that we land in C is almost the same when the database is X as it is when it is X prime. What is almost the same? It's e to the epsilon. For epsilon less than 1, this is about 1 plus epsilon. Okay? So it's almost the same. The ratio is bounded by e to the epsilon, or 1 plus epsilon. Okay, okay, so first of all, I claim this is an extremely general and broad definition. Let's go back to the medical insurance as an example. But you can fill in your own example. I'm just picking that one out of a hat. I'm going to go and apply for medical insurance, and one of the things that's going to happen before the insurance company tells me how much I have to pay is they will consult this database. Okay. From my point of view, there are good outcomes from this database and bad ones. The good ones give me lower insurance premiums. The bad ones give me higher insurance premiums. So here are the bad responses. I mean, it's, right, there are some. I don't need to know anything about them. Differential privacy says the chance that it will land in a bad response when I'm in the database is essentially the same as the chance that we land in a bad response when I'm not in the database. So I may as well contribute my data to the database. We want a definition that will encourage people to contribute because, as you all know from machine learning, more data helps. It just plain helps. So we want to encourage learning, the ability to learn, and for that we need people to contribute data. But we don't really want the effect to happen until lots of people come in. Okay. All right. Yes?
So you were saying that irrespective of the person who smokes or not smokes,
Yeah.
the probability that he is paying a big premium should be small.
What I'm saying is that if you're going to have a statistical database, and you want to encourage people to join it, then what they pay in medical insurance should not change very much. Should be essentially the same, independent of whether they join or not. If you're asking me whether I think it's right for medical insurance companies to be able to charge more for people who do smoke, typically they find out that you smoke by asking you directly, not by going to some other statistical database. And, you know, in the age of Obamacare, I shouldn't have to be answering that other question. It's a different question. What I want to do is I want to encourage people to contribute their data for medical research. Okay. So I said that a lot of the failings in the past were definitional failings. I've now given you a definition. Why is my definition different from the others? Why is it special? You know, you should be skeptical. Other people came with definitions they liked too. Why is this one different? So first of all, it addresses risks beyond re-identification, such as the higher insurance premiums question. Why? Because again, the probability that I have to pay more is essentially independent of whether I'm in the database or not. Now, I said that it neutralizes all linkage attacks, like the IMDb attack. Why? Because this guarantee here it's a guarantee about the algorithm. Again, the probability spaces here are the coin flips of the algorithm, of the algorithm M, or the curator. It's not probability over the random draws of who ended up in the database. No, it's the coin flips of the good guys, the algorithm. This behavior is going to hold no matter what some possible attacker or data analyst knows or doesn't know. Right? Whether or not they have access to some extra information, it's irrelevant. This behavior still holds. So it neutralizes the linkage attacks. If you can't link when I'm not in the database, you certainly, I mean, if you can't, yeah, right. It guarantees that if you can't link when I'm not in the database, which you obviously can't, then you can't link when I am, because the ratio of those probabilities, one of them has a 0 in the denominator. You just wouldn't be able to do it. Okay. What does that mean? It means that this is a promise that can be made not only independent of what the adversary currently knows, but it's made independent of what the adversary can learn any time into the future. Still, you cannot carry out a linkage attack. Now, the only thing I did here was I moved this term from over there to the denominator and just divided both sides by the probability that m of x prime is in C. Then I took logs, and I'm going to call this the privacy loss when the database is x and x prime is any neighboring database. This is the privacy loss. So the guarantee is that the privacy loss is bounded by epsilon. Yes?
Here we are not in the situation where the analyzer asks multiple questions, right?
Wait. Sorry.
Here, are we in the
Okay. Yes and no. I haven't explained why or how, and for now it's easier to think of a single query, but we will talk about what happens over multiple queries and how to arrange that multiple queries also have a cumulative privacy loss of epsilon. But that's jumping ahead. Give me just a little time.
I just want to clarify. So the M is that entire encoding that the curator will do?
Yes, yes. It's the entire behavior of the curator as long as this database is alive. That's the long-term view. Okay. But for now, just think about it as a single query. We will get to multiple queries. Okay, so this is the definition of privacy loss. It's the log of the ratios, worst case log of the ratios. So the promise in differential epsilon 0 differential privacy is that the privacy loss is bounded by epsilon. So we have quantified our privacy loss. It's not just binary yes or no, this is private or not private, but no, there's this amount that we can associate things. This allows us to carry out meaningful comparisons of techniques. We can take two different techniques that have the same epsilon guarantee and different accuracies, and we can say the more accurate one is better. Or we can take two different things that have the same accuracy and look at how do their epsilons compare, how do their privacy losses compare, and say this one is better or that one is better. So we'll give an example later in the talk today of one of these comparisons. All right. Another thing is that composition is unconditional and automatic. If I have two different databases, one of which is epsilon 1 differentially private and the other is epsilon 2, then the world as a whole, that's the combination of those two things, is at most epsilon 1 plus epsilon 2 differentially private. Similarly, if the database answers one query with epsilon 1 differential privacy and the next query with epsilon 2 differential privacy, then the cumulative harm is bounded by epsilon 1 plus epsilon 2. And this is very easy to see. It's just straightforward writing things out. We simply define a mechanism which is the pairing of M1 and M2. And the probability that we get R1, R2 when we run these two guys is the probability that when the database is D, we get R1, and D, we get R2. And in the denominator, when the database is D prime, we get R1, and when it's deprived, we get R2. The stuff in blue is bounded by e to the epsilon 1. The stuff in black is e to the epsilon 2. The epsilons add up. Okay. This is called simple composition. Later, we'll see a more advanced composition. So notice that this is a property of the definition of differential privacy, not the implementation. This is something that you get for free just from the definition. Okay. So we've seen that this allows us to understand cumulative privacy loss if you're answering many queries with certain loss each, or if there are different databases, each with their own losses. We are computer scientists. What do we love to do in terms of computing? We like to take simple primitives and build complicated things out of them. This allows us to analyze the privacy loss of complicated analyses, carry out complicated analyses by understanding the loss, the privacy loss at each of the steps. So this is where we're taking advantage of the fact that it's not just Boolean, yes private, no private, it's here's an amount and now we can see what happens over multiple instances. Here's one final property, which is that we naturally get group privacy. So let's say that we want to protect not just the privacy of whether I'm there or not, but also whether Satya is there. And the two of us, like we're both in or we're both out. If the mechanism is epsilon differentially private, then it gives privacy for pairs of people at a rate of 2 epsilon, just simple composition. So one of the things that this means, which I'm not sure why I felt it was necessary to tell you this right now, but any output that's possible on one database will be possible on any other database, although its likelihood may be completely different. But you can't have 0 probability on one database when you have non-zero probability on another. And that follows from the composition theorem, the group privacy. Okay. How do you do it? Well, of course, there are multiple ways. We'll talk about first one that you probably already know. Here's something that's absolutely none of my business, right? I want to count how many people did this thing last night. So when I ask this question, did you do this last night? You don't give me the straight answer right away. No. First of all, you flip a coin. If the outcome is heads, then you're going to answer randomly. You flip a second coin and you tell me yes if the second coin is heads and no if it's tails. But if your first coin came up tails, you're going to answer honestly. Now don't tell me the result of your first coin. So when you say yes, I don't know whether you're bragging or whether, no, you just flipped a coin and it said to answer randomly, and you flipped again and you got heads the second time. Same with an answer of tails. So I'm claiming this is differentially private for some value of epsilon. So the probability that you say yes when the truth is yes, divided by the probability that you say yes when the truth is no, you can work it out, that's 3. And similarly for the answer of no. So this is log of 3 differentially private. Now notice here a very important point. There are no sort of good outputs and bad outputs. If you look at the statistics literature on confidentiality, there's a tremendous discussion of this would not be a safe output to produce. But no, here the privacy is by the process by which we got this output. It was the fact that there was this randomization that gave you the privacy. By the way, this technique, randomized response, was developed in 1965 by Warner in the social sciences to allow study of embarrassing or even illegal activity. Okay, oh, I jumped ahead and I said this. So it's ln 3 differentially private. Great. Here's another technique. This is going to be the Laplace mechanism. So let's look at this probability distribution. It's a two-sided exponential distribution. It has a parameter b. And it says that the density at any z is exponentially small in the magnitude of z divided by b, also divided by 2b. I'm going to be looking at ratios of probabilities. You saw that in the definition of privacy loss. So this last fraction in this division by 2b is going to happen in the numerator and the denominator. I'm never going to mention it again. Forget it from now on. We'll always be looking at things like this. Okay, so the variance of this is 2b squared. So that means that if we make b bigger, we'll flatten the curve, and if b is smaller, we get a sharper peak. So here's our first seriously new mechanism. This first time is just, we're looking at real valued functions f. So we're going to define the sensitivity of f to be the maximum amount over all possible databases by which the presence or absence of one person can change the outcome f. So we look at the maximum over all adjacent databases x and x prime of the absolute value of the difference between f of x and f of x prime. If we're trying to hide the presence or absence of that one person who makes the difference between x and x prime, we're going to have to somehow hide something as big as delta f. Okay? So the theorem says if you want to achieve epsilon differential privacy, it's sufficient to add noise that's scaled to draw from the Laplace distribution where the parameter is the sensitivity divided by epsilon. So let's look at that. If the sensitivity is very small, meaning my presence or absence changes the outcome very little, then we don't need a lot of noise to hide whether I'm there or not. Similarly, if I want really good privacy, which means epsilon is very, very small, then I need a fatter curve, a bigger addition of noise. So better privacy, or smaller epsilon, will mean more distortion. We will prove this in a moment, but we'll actually prove a generalization. So again, just to be really clear what the technique is, the curator, when it's given the query f, computes f on the database. Then the curator samples the Laplace distribution, Laplace of the sensitivity of f divided by epsilon. It gets a real number. It adds that to the true answer, and that's what's released. Okay, is it clear? Okay, now let's go back to our counting queries, the same question that we had when we were looking at randomized response. The sensitivity of a counting query is only one. My being there or not being there can change the outcome of how many people in the database XYZ last night by at most one. Or for any property, how many people in the database have property P? Well, the presence or absence of one person can change the answer to that how many people in the database question by at most one. So what this says is, to handle counting queries, it's sufficient to add noise that is drawn according to Laplace of 1 over epsilon. We expect that thing to look like about 1 over epsilon. There was that 1 over 2b thing, which I said forget about. Well, this is kind of cool, because suppose that you were like running a survey, and so you collected n people in order to find out what fraction of the population had property P. You'd have a sampling error that looks like square root of n. We're adding noise that's way smaller than the sampling error. We're adding constant noise as opposed to the noise you get in random sampling. So we're really getting privacy for free. Now, in randomized response, the error that you get would be something like the sampling error. You get a square root n-ish error. In the Laplace mechanism, for the same epsilon, we're getting a constant error. So the Laplace mechanism is better than randomized response. And we're using our ability to compare two algorithms. Yes?
Can you explain how this Laplace mechanism applies to the initial example of single bit? So there is a that if we have some noise, then we can figure out the...
So that is a question of multiple counting queries. And we will talk a lot about how to handle many counting queries, but not quite yet. I will get to it. If you were handling, yeah, I will get to it. Just let me stop there for at least until the next slide. Okay. Vector valued queries. So I was talking before about real valued queries, but now I can have a query whose answer is in d-dimensional space, which is somewhat the same as asking d queries if they don't have to be chosen adaptively. That's getting to your question. But I'm not going to give you a 100% satisfactory answer yet. What this theorem says is, the theorem is the same as the old theorem, except in, well, two regards. First of all, I've generalized the definition of sensitivity to be the L1 difference, so the sum of the absolute values of the differences in each component, okay? Which, for the case of just d equal 1, is exactly the same. And so what the theorem says now is, on query F, to achieve epsilon differential privacy, it suffices to add scaled symmetric noise where I have, in each of the d-dimensional outputs, a fresh random draw from this variable. Okay? So, so if I wanted to answer 10 queries, 10 queries, I could view it as a 10-dimensional thing, and I could sample with 1 over epsilon, 1 over epsilon for each of these different components. No, I lied. One person could affect all of those counts. So the sensitivity there would be 10, not 1. And we will get back to that. That's very important. Okay. All right, so why does this work? Let's look at a particular output, say T, and pretend that I had written density instead of probability. Okay. So I want to know, what's the ratio of the chance that I'm going to see T when the database is X versus when it's the adjacent X prime? When it's X, that probability is going to scale with T minus f of X in the exponent divided by the parameter to the Laplace. When it is X prime, that probability is going to scale with T minus f of X prime divided by this delta f over epsilon. All right? Now, we're going to use the triangle inequality here to get this thing bounded by delta f. That's the definition. So we're going to have a delta f in the numerator, and we're dividing by delta f over epsilon. That's going to give us an epsilon. Very, very simple. This is why it works. Okay, so we have a theorem. And when we tried to apply it to very large numbers of queries, we still don't really like the outcome. But we've got something really interesting here. And this observation, which is due to Adam Smith, was kind of let me know that we were onto something. So a histogram query. A histogram query is the following. We have a set of database elements. We have a universe from which the database elements are drawn. In the histogram query, we partition the universe into disjoint cells. And what the query is asking is, for each of these cells, how many people in the database live in this cell, this cell, this cell, this cell? So in my example, I think I have 11 cells here, and the implicit question is, how many people in the database live in this cell? How many people live in this cell? How many people live in this cell? And so on. Is the question clear? So it looks like we're asking many counting queries. 11. But since the histogram is a partitioning of the universe of possible people, each person can only live in one cell. So my presence or absence can change the outcome to the histogram query in only one cell, and that cell only by one. So the sensitivity of the histogram query is just one, independent of how many cells there are. And this is very powerful. So it says that it's enough to add noise that's scaled to 1 over epsilon, rather than the number of cells over epsilon. The noise doesn't have to be dependent on the number of cells at all.
So what is D here?
D was the dimension, how many
Yeah,
cells?
okay, but in case of histograms, so you said that D queries is equivalent to a query in the D dimension, right?
It can be viewed that way, yes. Uh-huh.
Okay.
So
If the D numbers are membership values, then they are dependent. So if we
yeah.
Also, since one person belongs to one cell, so D.
Right, right. So if the cells are, over 5 feet tall versus under 5 feet tall, well, either I'm over 5 feet or I'm under 5 feet, but I can't possibly be both. So my presence or absence can only affect one count. We don't know which one, but just one. Okay. So when you kind of sit down and do the math, and we will, but not right now, it lets you do a lot of things. For example, you can answer the question, here's a list of 10,000 first names. So each person only has one first name. Here's a list of 10,000 first names. Which ones were the most popular in the 2010 census? Well, I might not get exactly the right answer. If there are 2 names that have very similar popularity, when I add the random noise, the slightly less popular one might look a little more popular. But I won't get big mistakes. So what this says is, say, with epsilon equal to 1, with probability 0.95, my cell count estimate will not be wrong by more than about 12 in any cell. So I can get a pretty good answer to which was the most popular names, or which were the most popular names. One more technique. What happens if f is just some insanely mysterious function that you don't understand at all and you certainly can't find the sensitivity of? Is it hopeless? Not necessarily. It might be, but there are some cases where it might be, but there are some cases in which it isn't. Suppose our function that we want to compute is one that, in some sense, does well when you subsample. It gives you a pretty good estimate when you subsample. There are several such functions. So what happens in this technique is you take your database and you partition it into blocks. So here I've got 4 disjoint blocks. What I'm going to do is I'm going to compute my function on each of these blocks independently. So now I have 4 different answers. and I'm going to aggregate them in some way. Well, depending on what we're doing, you might choose different, one aggregation function or another. What you need to do is choose a differentially private aggregation function. If you can do this, then you get a differentially private estimation. And here's why. So, you only need to understand the function g. You don't need to understand the function f. One person is only going to land in one of these cells in the partitioning. That means that one person will only change one of the inputs to this differentially private aggregator. And then you use the differential privacy of the aggregation to say that you can't tell whether this is even there or not. Okay. So the point is that if the aggregator is differentially private, then the whole mechanism is. Finding really, really good applications for this technique, some success in the literature, not a phenomenal amount of success. My personal belief is that the power of this is very, very strong, and that its full glory remains to be developed. We'll see for fun one application in the very last lecture, which is really surprising. Okay, thank you.
We should break for tea.
No, that's clear. Yeah. Maybe you have questions.
Yeah, if you have questions.
Right now, we can ask questions.
An hour and a half is a long lecture. So.
You can take a break.
No, I mean for the people in the room.
The future lectures, if you want to
Okay.
break in the middle, that's fine.
All right. My father was a math professor, and he once told me that anybody who talks for more than an hour should be shot. So I feel guilty. But thank you for your attention.
Normal distribution doesn't work because it has x squared.
A normal distribution doesn't work. However, we will discuss it because it has some interesting properties. And there's a relaxation that we use it with sometimes. We'll talk about that in lecture 3.
We are actually trying to put our data as an order distribution. We actually project our results as an order distribution.
I don't understand. You're projecting your results.
We say that
You're trying to fit your results to a normal.
yeah.
Mm-hmm.
So that is the way you try to hide the privacy of this.
But the wish is according to the process. The noise is not
That
overall.
is actually making a person not visible because that person can be at any of the ends of that graph.
Let's talk about this offline. Okay? Yeah. Mm-hmm.
What a group query?
I'm sorry?
Group query.
A group query.
So if the group is size k,
Yes.
then it is an error of k of them, right?
Yes.
So, but we also submit said that the error is only zero even if we have several queries.
Right.
So how does that, how do these two things match?
So, in some funny way, for pure epsilon zero differential privacy, things behave very similarly. We will soon move to a relaxation of differential privacy, which works nicely for multiple queries, but is not so good with sets of size k.
So what is the difference between multiple queries and size k? Aren't they the same thing?
They're not exactly the same thing mathematically. For the version of the definition that I gave you, they're very, very similar. But in general, they are not that similar. We will see this.
And we said something that when we said about going beyond re-identification, I think then I did not understand how is it really beyond re-identification? So aren't we using the same thing that
Well, we don't even release data records. We simply answer statistical queries. So there are people who work with data. I mean, official policy will say that all you need to do is protect against re-identification. Now, we say that when you release what's called microdata, there are worries beyond re-identification, like the example with the elderly neighbor.
So I want to know that why is it different from re-identification? Is it the same? So we are identifying that this person has something. That's the same thing.
No, re-identification, as I said, means taking exactly this data record and matching it to the person that it came from. The reason you don't want to allow re-identification is to prevent somebody from learning stuff, right? But the real issue is learning stuff. So if you have a technique that prevents re-identification but still allows intimate details to be learned, it's a bad technique. So you need a protection that goes beyond protecting against re-identification. And that was what we offer. Other questions? Okay, thank you.